morning, everybody. Today let us discuss about parallel transform and respected impedance. So coming to ideal transformer. An ideal transformer is a unity coupled. Unity coupled means K is equal to 1. It means tightly coupled. Okay. Right? And lossless transformer having no losses, in which the primary and secondary coils have infinite self-inductance. Means L1, L2, M. Okay, all are equal to infinite. Okay. So an ideal transformer is a unity coupled circuit. Means K is equal to 1. Means let us have two coils. This is primary coil, whereas this is secondary coil. So when K is equal to 1 means whatever the flux is produced in coil 1, all flux will link coil 2. So similarly, whatever the flux is produced in coil 2, all flux links coil 1. Okay, then K is equal to 1. So K is equal to 1, right? So in ideal transformer, K is equal to 1 and lossless. Okay, ideal transformer is lossless. Means R1 is equal to 0 and R2 is equal to 0. R1 is equal to 0 means R1 is the resistance of primary winding. R2 is the resistance of secondary winding. Okay. Having no resistances. Okay, R1 and R2 will be 0. K is equal to 1. L1, L2, M will be infinite. Coils have very large reactances. Means L1, L2, M or infinite. Iron core transformer are close approximations to ideal transformer. Okay, because almost K is nearly equal to 1. Okay, almost whatever the flux is produced in coil 1, all flux links coil 2. Okay, that's why iron core transformer are close approximations to ideal transformer. Okay, this is iron core transformer. Okay, the medium which is present between these two coils is iron. Okay, that's why it is called iron core transformer. Okay, here these transformers are used in power systems and power electronics. Okay, so here this means indicating these two lines means this is iron core transformer. This is iron core transformer. This indicates these two lines indicate iron core. This is a supply voltage given to the primary winding. This is the secondary winding. Load is connected to the winding. The winding to which the load is connected is called secondary winding. The winding to which supply is given to this winding is called primary winding. Okay, here this, when a sinusoidal voltage is applied to the primary winding, as shown in the figure, the same magnetic flux phi goes through both windings. Okay, means right? Phi is the flux which is produced in coil 1, which is equal to phi 11 plus phi 12. Okay, this is the flux which is linking both coils. Right? What is the induced EMF in coil 1? V1 is equal to N1 d phi by dt. Let total flux phi is the flux which is linking both coils, in ideal transformer. In ideal transformer, K is equal to 1. K is equal to 1 means phi is the total flux which links two coils. Okay. This is the case which is in practical transformer. Okay. In ideal transformer, phi is the flux which is produced in coil 1. This flux links coil 1 as well as coil 2. Okay, then what is the EMF induced in coil 1? V1 is according to the Faraday's law of electromagnetic induction, V1 is equal to N1 d phi by dt. Similarly, what will be the EMF induced in coil 2? Because of flux which is produced in coil 1. Okay, this is a flux which is linking coil 1 as well as coil 2. Okay, because of this flux, EMF will be induced in coil 2. Okay, that EMF is V2. V2 is equal to N2 d phi by dt. Okay, so divide this equation by this equation, then you are going to get V2 by V1 is equal to N2 by N1, which is equal to N, small n, where small n is turns ratio or transformation ratio. It is called as turns ratio. It is also called as transformation ratio. So V2 by V1 is equal to N2 by N1 is equal to N, where N is transformation ratio or turns ratio. For the reason of power conservation, okay, input power is equal to output power. Okay, power in primary winding is equal to power in secondary winding, or the energy supplied to the primary must equal the energy absorbed by the secondary. Power supplied by primary is equal to power received by secondary, absorbed by the secondary. Okay, so V1 I1 is equal to V2 I2. Okay, from this we can write I1 by I2 is equal to V2 by V1 is equal to N. Okay, already you know V2 by V1 is equal to N2 by N1, N2 by N1, which is equal to N. Okay. For the reason of power conservation, V1 I1 is equal to V2 I2. Then you're going to have I1 I2 by, sorry, I1 by I2 is equal to V2 by V1 equal to N. You can write I2 by I1 is equal to N1 by N2 is equal to 1 by N. When N is equal to 1, we generally call the transformer an isolation transformer. If N is greater than 1, okay, you know, right, what is transformation ratio? V2 by V1. V2 by V1 is equal to N2 by N1, which is equal to N, which is equal to I1 by I2. I1 by I2. Okay, if N is greater than 1 means, if N is greater than 1 means V2 will be greater than V2. Sorry, V2 is greater than V1. If N is greater than 1 means V2 is greater than V1. Okay, if V2 is greater than V1 means that the type of transformer is called step-up transformer. Okay, if secondary voltage is greater than primary voltage, then the transformer is called step-up transformer. If the primary voltage is greater than secondary voltage, then the transformer is called step-down transformer. Okay, so if V2 is greater than V1, then the transformer is called step-up transformer. If V1 is greater than V2, then the transformer is called step-down transformer. Step-down transformer. Okay, meaning of this is secondary voltage is greater than primary voltage. Coming to this, primary voltage is greater than secondary voltage. A step-down transformer is one whose secondary voltage is less than its primary voltage. A step-up transformer is one whose secondary voltage is greater than its primary voltage. The ratings of transformers are usually specified as V1 by V2. A transformer with rating 2400 by 120 volts should have 2400 volts on primary side, 120 volts on secondary side. Means here V1 is greater than V2. V1 is greater than V2. If V1 is greater than V2 means then the transformer will be step down transformer. Then the transformer is step down transformer. That is secondary voltage is less than primary voltage. Then the transformer is called step down transformer. Coming to dot convention applied to ideal transformer. Here we have two statements to determine the voltage polarity. If V1 and V2 are both positive, if V1 and V2 are both positive or negative at dotted terminal, if here see coming to case A, in this case V1 is positive at dotted terminal, V2 is also positive at dotted terminal. If V1 and V2 are positive at dotted terminal or negative at dotted terminal, then we use plus n. We use plus n. Otherwise, use minus n. Otherwise, use minus n. Okay. So in this case, V1 is positive as well as V2 is positive at dotted terminal, right? So we use plus n. We have to use plus n. And then you know, right? V2 by V1 is equal to N2 by N1. N1 which is equal to n, which is equal to n. Okay, that's why here we use plus n. V2 by V1 is equal to N2 by N1. Okay. Coming to this case, here V1 is positive at dotted terminal, V2 is also positive at dotted terminal. That's why we used plus n. V2 by V1 is equal to N2 by N1. Coming to this case, case C. Here V1 is negative at dotted terminal, V2 is positive at dotted terminal. Then we have to use minus n. Okay, here see. If V1 and V2 are both positive or negative at dotted terminal, then we use plus n. Otherwise, we have to use minus n. Here, both voltages are not positive or negative at dotted terminal. Okay, one voltage is negative at this dotted terminal, another voltage is positive at this dotted terminal. So we have to use minus n. So V2 by V1 is equal to minus n. Minus n means minus N2 by N1. Coming to last case, here V1 is positive at dotted terminal, V2 is negative at dotted terminal. Means both voltages are not positive at dotted terminal, not negative at dotted terminal. So we have to use minus n only. So V2 by V1 is equal to minus N2 by N1. Coming to current ratio, here coming to statement 2, if I1 and I2 both enter into or both leave the dotted terminals, then we have to use minus n. If I1 and I2 are entering the dotted terminal or leaving the dotted terminal, we have to use minus n. Otherwise, we have to use plus n. Okay, here see, let us look into this case 1. Here I1 is entering, I2 is leaving. Means we have to use plus n. If both are entering or leaving the dotted terminals, then we have to use minus n. Okay, here see, one is entering and the other current is leaving. So we have to use plus n. Here one is entering and the other one is also entering. So here in this case, both currents are entering the dotted terminal, means we have to use minus n. So I2 by I1 is equal to minus n is equal to minus n1 by n2. Next here, coming to this case, coming to case C, I1 is leaving the dotted terminal, I2 is entering. Okay, that's why we have to use plus n. Here I1 is entering, I2 is also entering. If I1 and I2 are entering or leaving the dotted terminals, then we have to use minus n. Otherwise, we have to use plus n. So here, in this case, I1 and I2 both are entering the dotted terminal. So we have to use minus n. So I2 by I1 is equal to minus n is equal to minus n1 by n2. Coming to power in the transformer, we know, right? V2 by V1 is equal to n. N is transformation ratio. N is equal to N2 by N1, right? So V1 is equal to V2 by n. Okay, V2 is equal to n V1. Similarly, I1 is equal to n I2. You know, right? N is equal to N2 by N1, which is equal to I1 by I2. I1 by I2. Okay, so I1 is equal to Ni2 or I2 is equal to I1 by N. The complex power in the primary winding is V1 I1 conjugate, which is equal to V1 can be written as V2 by N into I1 conjugate can be written as Ni2 conjugate, which is equal to this is nothing but what? This is V2 only. V2 Ni2 by N means you're going to get I2 conjugate. So you're going to get S2. So S1 is equal to S2. Complex power in primary winding is called complex power in secondary winding. The transformer absorbs no power. So coming to this problem, an ideal transformer is rated at 2400 volts by 120 volts, 9.6 kVA, and has 50 turns on the second side. Calculate the turns ratio, the number of turns on primary side, and the current ratings for the primary and secondary winding. Okay. Here, power rating is given, voltage ratio is given, and then number of turns is given. Number of turns on secondary side is given. That is N2 is equal to 50. So we know, right? V2 by V1 is equal to N, which is equal to 120 by 2400. You're going to get 0.05. You know, N is equal to N2 by N1. This value is given. N2 is given. If N2 is given means you can get N1. Okay, N1 is equal to 50 by 0.05 is equal to 1000 turns. You know, right? S is equal to, V1 I1 is equal to V2 I2, which is equal to 9.6 kVA. Transformer is a constant power device. The power will be constant. Primary power in primary winding is equal to power in secondary winding. So V1 I1 is equal to V2 I2, which is equal to 9.6 kVA. It is given, right? From that we can find I1. I1 is equal to power P by V1. You are going to get 4 amps. I2 is equal to power by V2, which is equal to you are going to get 80 amps. Okay, from this you can find I2. It's analysis of circuit containing ideal transformer. Next, you're going to find reflected impedance. Reflected impedance is what you're going to do is you're going to shift this impedance to primary side. Okay, whatever the impedance is present in the secondary side, you're going to shift that impedance to primary side. Okay, here, Z in input impedance, which is equal to V1 by I1. You know, right? V1 by I1. V1 is equal to V2 by N. I1 is equal to Ni2. So from this, you are going to get 1 by N square V2 by I2. Then Z in is equal to ZL by N square, where ZL is equal to V2 by I2. Load impedance between these two terminals. Load impedance between these two terminals is equal to V2 by I2. V2 by I2. Load impedance ZL is equal to V2 by I2. You know Zin. Zin means input impedance between these two terminals. That is equal to V1 by I1, which is equal to V2 by N by Ni2, which is equal to 1 by N square into V2 by I2. Okay, you know, load impedance is equal to V2 by I2. Okay, from this you can find Zin is equal to ZL by N square. Okay, the input impedance is also called the reflected impedance. This impedance is called reflected impedance because we are shifting this impedance to primary side. Since it appears as if the load impedance is reflected to the primary side. We are shifting the secondary impedance to the primary side. That's why this impedance is called reflected impedance. This ability of the transformer to transform a given impedance into another impedance provides us a means of impedance matching so that we can find maximum power delivered to the load. Maximum power will be delivered to the load when source impedance is equal to load impedance. We are going to derive this. We are going to get reflected impedance using Thevenin's theorem. Okay. Here, first you find the Thevenin's equivalent of circuit to the right of terminals. Means you are going to find Thevenin's voltage between these two terminals. Then you are going to find Thevenin's impedance between these two terminals. Okay. So here VTH, finding VTH. VTH means here these two terminals are kept open, so that's why the voltage between these two terminals is open circuit voltage, that is equal to VTH. When these two are open means I1 will be 0. When I1 is 0 means I2 will be 0. That's why I1, I2 both are equal to 0. Okay, so here VTH is equal to V1. VTH is equal to V1. This is equal to V2 by N. You know, here transformation ratio is 1:N. Okay, that's why V1 is equal to V2 by N, which is equal to Vs2 by N. Here V2 is equal to Vs2. Anyhow, I2 is 0. If I2 is 0, voltage between these 2 points is equal to Vs2. So here ZTH. ZTH, in order to find ZTH, let us use a unit source. Let us use a unit source. Okay, that is 1 at an angle 0 degrees. Let us use 1 at an angle 0 degrees in order to find ZTH. Okay, when you use this test cell, okay, when you use this test cell, you make all of the sources 0. So this is replaced by short circuit. Okay, this is replaced by short circuit. Okay, only Z2 is present in this circuit. Okay, this is replaced by short circuit. So this test cell is connected between the terminals A and B. Okay, now ZTH is equal to V1 by I1. You know, V1 is equal to V2 by N. I1 is equal to N I2. So you're going to finally you're going to get, you know, V2 by I2 is equal to Z2. Z2. Okay. So Z2 by N square. Finally you're going to get Z2 by N square. Okay. When you're going to shift this impedance to primary side, then that impedance will be equal to Z2 by N square. So here you are shifting this impedance. Okay, you are shifting the source also. Then Z2 by N square. Okay, Vs2 by N. You know, right? VTH. VTH is the voltage between these two terminals. Voltage between the terminals A and B. Okay, so Vs2 by N. Vs2 by N. That's why when Vs2 is shifted to primary side, then this voltage becomes Vs2 by N. When this impedance is shifted to primary side, this impedance becomes Z2 by N square. The general rule of eliminating the transformer and reflecting the secondary circuit to the primary side is dividing the secondary impedance by N square. Okay, you have to divide this secondary impedance by N square. Okay, the reflected impedance is Z2 by N square when it is reflected to primary side. Divide the secondary voltage by N. Multiply the secondary current by N. Coming to this problem. For the ideal transformer circuit, the source current I1, the output voltage V0, and the complex power supplied by the source. You have to find all these. The source current I1, V0, complex power supplied by the source. So this is the given circuit. So what we do is, let me shift this resistance to primary side. Let us find reflected impedance. If it is reflected to primary means resistance by N square, Z by N square, right? So 20 by N square. So you're going to get 20 by 4. Okay, anyhow n is given. Okay, 20 by 4, which is equal to 5 ohm. Okay, then what will be the total impedance? This is shifted to, this Z2 is shifted to primary side. Okay, then you're going to get Z2 by n square. Again, this voltage will be shifted to primary side. Then Vs by n. Okay, then Zn is equal to 4 minus J6 plus the impedance which is shifted to primary side. That is Zr. Okay, plus Zr. You're going to get this. Okay, what will be I1? I1 is equal to 120 at an angle 0 degrees by input impedance. Total voltage by input impedance. Okay, what is the input impedance? Input impedance is 10.82 at an angle minus 33.69 degrees. Okay, then you're going to get this I1. Okay, you got I1. You got the value of I1. Okay, since both I1 and I2 leave the dotted terminals, leaving the dotted terminal, right? Here see, I1 is leaving the dotted terminal, I2 is also leaving the dotted terminal. Okay, if both are leaving or entering the dotted terminal, we have to use minus n. We have to use minus n. Then I2 is equal to minus I1 by n, which is equal to this much. You know, V0 is equal to 20 I2. V0 is equal to 20 I2. This is equal to, with the complex power supplied is S is equal to PS, source voltage, source current, conjugate. Okay, Vs I1 conjugate. Then 120 at an angle 0 degrees, 11.09. Okay, here where is I1? Okay, I1 is 11.09, that is at an angle 33.69 degrees. Then what will be I1 conjugate? I1 conjugate will be 11.09 at an angle minus 33.69 degrees. Then you are going to get this. Here, if we have take it like this, here dot is placed here, here one dot, here another dot. Between these two, 2 milli mutual inductance is 2 millihenry. Between these two, between this coil and this coil, between this coil and this coil, it is 10 millihenry. 10 millihenry. Then what will be the equivalent inductance, L equivalent, between these two? If L1 is equal to 4 millihenry, L2 is equal to 6 millihenry, L3 is equal to 5 millihenry. Then L equivalent is equal to L1 plus L2 plus L3 between these two. There is no mutual inductance between these two coils. Mutual inductance is present between these two coils as well as these two coils. Okay, so between coming to these two coils, there is no mutual inductance present between these two coils. Coming to these two coils, current is leaving the dot terminal here. Current is entering the dot terminal. Okay, so here current is leaving, current is entering. Means these two are series opposing. Means you are going to get minus 2 M, you can say M23, M23. Now coming to this one. Here current is entering the dot terminal. Here also current is entering the dot terminal. Current is entering the dot terminal. Current is entering the dot terminal. Both are series aiding. Series aiding. Okay. Then plus 2 M to take 13 M13. Okay. Which is equal to L1 is 4 millihenry plus L2 is 6 millihenry. L3 is 5 millihenry plus minus 2 into what is M23? M23 is 2. Okay, plus what is M13? 2 into 10. 2 into 10. Okay, 20 minus 4, 16. 16, 20, 11, 31. 31 millihenry. If you have like this, two coils, dot is placed here, dot is placed here. These two coils are aiding each other. This connection is called series aiding connection. Okay, then L equivalent is equal to what? L equivalent is equal to L1 plus L2 if M is the mutual inductance between these two coils. Then plus 2M. Again, we have series aiding connection. Current is leaving the dot terminal. Again, current is leaving the dot terminal of coil 2. Okay, then again you are going to have same formula. L equivalent is equal to L1 plus L2 plus 2M. Okay. Here current is entering the dot terminal, leaving the dot terminal. Here current is leaving the dot terminal, entering the dot terminal. Means there this connection is called series opposing connection. Means L equivalent is equal to L1 plus L2 minus 2M. Minus 2M. I'll explain one connection. Current is entering. Current is entering. So total voltage at this point with respect to this point is total voltage. Then total voltage P is equal to nothing but L equivalent D I by dt, which is equal to L1 di by dt, L1 di by dt plus V1. You're going to find V1. V1 is voltage across this, V2 is voltage across this. Okay, V1 is voltage at this point with respect to this point. V2 is voltage at this point with respect to this point. Right? So first L1 di by dt is self-induced EMF in coil 1. Coming to mutual induced EMF in coil 1. Okay, let M is mutual inductance between these two coils. Okay, here see current is entering the dot terminal of coil 2. If current is entering the dot terminal of coil 2 means mutual induced EMF will be positive at dot terminal. Positive at dot terminal means we are going to anyhow you are collecting voltage at this point with respect to this point. Means mutual induced EMF will be M E I by dt plus V1 is connected. Coming to V2, okay. Self-induced EMF is L2 d I by dt plus what will be the mutual induced EMF across coil 2? Here current is entering the dot terminal. Current is entering the dot terminal of coil 1 means mutual EMF will be positive at dot terminal. Okay, then we're going to correct positive voltage, positive mutual EMF, MA by PT. Then finally you're going to get L equivalent is equal to L1 plus L2 plus 2M. Let me use series opposing connection. Okay. Dot is this here. Dot is this here. This series opposing connection. Let I is the current flowing through this. L1 is self-inductance of coil 1, L2 is self-inductance of coil 2. M is mutual inductance between these two coils. Then V is equal, total voltage is equal to L equivalent di by dt, which is equal to, what is the self-induced EMF in coil 1? L1 di by dt. What is the mutual induced EMF in coil 1? Okay, let us find the mutual induced EMF, polarity of mutual induced EMF in coil 1. Here current is leaving the dot terminal. Current is leaving the dot terminal. Current is leaving the dot terminal means mutual induced EMF in coil 1 will be negative at dot terminal. This will be negative at dot terminal. Negative at dot terminal means you are collecting, anyhow you are collecting voltage at this point with respect to this point, means you are collecting negative voltage. Then you are going to get minus M d I by dt. Next, plus what is the self-induced EMF in coil 2? That will be L2 di by dt. What is the mutual induced EMF in coil 2? Here current is entering the dot terminal. Current is entering the dot terminal means mutual induced EMF in coil 2 will be positive at dot terminal. So this will be positive at dot terminal. So here it will be positive and it will be negative. Anyhow, you are collecting voltage at this point. With respect to this point, that voltage will be negative. So you are going to get minus M d I by dt. Then L equivalent is equal to what? L equivalent is equal to L1 plus L2 minus 2M. You can also use KVL equation like this. Here, current is entering, current is leaving. This connection is series opposing connection. Okay. Here current is leaving, current is entering. Series opposing. Current is entering, series heading connection. That's why here we use plus 2M, here we use minus 2M.